in previous class I was discussing you about crystal diode or PN junction diode. Okay, so suppose this is a PN junction diode. This is point A and this is point B. This is anode side and this is cathode side. So this diode can be represented in piecewise linear equivalent circuit or approximate model like this. This is V0 and this is RF. RF is the forward resistance of this diode and V0 is the contact potential of this diode. Okay, so V0 it is equal to say 0.3 volt, it is equal to 0.5 volt and it is equal to 1.2 volt depending upon the material that is used in making this PN junction diode. So it is for germanium PN junction diode, it is for silicon PN junction diode, and this 1.2 volt it is for gallium arsenide based PN junction diode. Okay, so V0 we have to replace with these voltages depending upon the material of the diode that is used. Okay, and this RF is the resistance offered by this diode in forward condition. Similarly, in case of simplified equivalent model or circuit, this can be represented or this has to be replaced with this in simplified model. Okay, V0 is, what is V0? Again, V0 is equal to this much. Now in case of ideal model, we can replace this diode. We can replace this diode with closed switch. This is closed switch. Closed switch or short. Okay, short in ideal model. Okay, if we are considering this PN junction as ideal diode, then in that case the resistance offered by the diode it is equal to 0 and V0 is equal to 0 in forward bias condition. So we can replace this diode like this or like this or like this depending upon the conditions. If we are assuming diode as ideal, then we can replace this diode with this model. If we are using simplified model, then we have to replace this diode with this model. Similarly, we can replace this diode with this model if we are assuming piecewise linear equivalent circuit or approximate model. Okay, so this is clear. Now we will study about load line analysis. So what is load line analysis? Okay, so in load line analysis, suppose the circuit is like this, any circuit. Suppose this is E0 and this is diode D, this is R. V0 can be measured across this R and this is ID, and okay, like this. So how we can determine ID, VD and voltage across this resistor by using graphical method. This can be done by using load line analysis. Okay, so in load line analysis, what we do, this is VD versus ID. This is the voltage of PN junction diode and ID is this current ID. Okay, so we have to plot load line. What is this load line and how we can plot it? See, here at this point it is it is ID, it is equal to 0 and it is equal to VDQ, and here ID is equal to E naught divided by R. It is ID, it is equal to IDQ. Okay, this load line, this is load line. Okay, now we can see that we can write down the current equation by using Kirchhoff's law. It is equal to E naught, it is equal to VD voltage that is dropped across this diode, and ID plus IDR. Okay, now there are two cases. First is ID it is equal to E naught minus VD divided by R. Now we have to determine ID when VD is equal to 0. So it will be equal to E naught by R. So if this VD, if VD is equal to 0, at in this axis, VD is equal to 0 in this axis. So ID it is equal to at this point. At this point it is equal to E naught by R. So it is represented as IDQ. It is equal to E naught by R. Now how we can determine VD? So VDQ it is equal to E naught minus ID into R. Under what condition? When ID is equal to 0. When ID is equal to 0, then the voltage it is VDQ. So we can write VDQ it is equal to E. So here ID it is equal to 0, and at ID is equal to 0, VD is equal to VDQ, and it is equal to E. So this point is this voltage E naught, this is E naught, okay, and this is E naught by R. Okay, so why it is known as load line? Okay, now this load line, it depends upon this load, the value of load R. Okay, now you can see how the value of R determines the slope of this load line. This is IDQ, and IDQ is equal to E naught divided by R. Okay, and this is VDQ, it is equal to E naught. Okay, and this is ID versus VD graph. This is load line. Now if the value of R varies, then the slope of this load line it will also vary. Okay, so depending upon the variation of this R, the slope of load line it also varies. That is why it is known as load line. Okay, so if R is lesser than this value, then what will happen? Then IDQ will be at this position like this. Okay, now if this R increases, what will happen? IDQ, its value will be lesser, so graph will be like this. Okay, so slope of this load line is dependent upon the value of R. That is why it is known as load line, and we can determine the current flowing through the diode and voltage across the diode by using load line analysis. So how we can determine it? You can see this graph. Suppose we have drawn the load line. Okay, this is E naught by R, and this is E naught VD versus ID. Okay, the circuit, this is for this circuit. This is R, diode D, current ID, and voltage across this diode is VD, and this is E naught. Okay, so this is E naught by R, this is E naught. Now we can draw the VI characteristics of this diode. This diode, suppose this is made up of silicon. Suppose this diode is made up of silicon. Then in that case, what will be this voltage? Knee voltage 0.7 volt. Okay, this is knee voltage. Okay, so this is ID versus VD. ID versus VD. Okay, so the diode current that is flowing through the diode, it is this point, and VD, it is this point. So by using graphical method, we can determine ID and VD. Rectifier, the main property of any diode is that it conducts in only one direction. Okay, so ID, if during forward bias condition, the current will conduct in this direction. Okay, and in opposite direction, it will offer a very high resistance, or it will be open in another direction. So a current flows in only one direction in case of diode. Okay, property of diode is used in rectifier circuit. So in rectifier circuit, AC signal is converted to DC. Okay, the main function of any rectifier circuit is that it converts AC signal to DC signal. Okay, so we will study about two types of rectifier. First one is half wave rectifier, and second one is full wave rectifier. Okay, so in this class we will study about half wave rectifier. This is the circuit diagram of half wave rectifier. Okay, so in this circuit, here it is transformer having turns ratio of N1, and say this is N2. N1 is the turns ratio of primary side, primary coil, and N2 is the turns ratio of secondary coil of the transformer. And this is AC main. Suppose this is 220 volts and 50 hertz line supply. This is transformer, this is step down transformer. So in step down transformer, suppose this is V2 and this is say V1. So what is the relationship between N1 and N2 for V1 and V2? It is N1 by N2, it is equal to V1 by V2. So you can write N2 by N1, it is equal to V2 by V1, which is equal to V2, it is equal to N2 by N1 into V1. So by using this equation, we can determine V2. Design a half wave rectifier circuit like this. Here this is V in, diode D, and this is RL. Okay. So here the magnitude of the input voltage should be very small, and here the transformer, here the step down transformer is used. So V2 is very much lesser as compared to V1, depending upon the turns ratio of the coil. Okay. Now, so V output will be equal to V input during positive half cycle. This is from 0 to T by 2. From this time period, 0 to T by 2, during positive half cycle, diode is forward bias, and we are considering diode as idle diode. So idle diode is replaced with short or closed switch. So all the voltage V output, it will be equal to this voltage that is appearing across this. Okay, so V output, it will be equal to V in, secondary voltage, that is Vs or V2 we can say. Okay. Now during T by 2 to T, the polarity across the secondary terminal, the polarity of the voltage across the secondary terminal, it changes. Now we can again connect the diode. This figure is for T by 2 to T. For T by 2 to T, the polarity of this secondary coil, it has changed. Now it is negative and this is positive. Okay, and this is P and this is N. So this is the configuration of reverse bias condition. So in reverse bias condition, an idle diode can be replaced as open. This is open. So we can replace this PN junction diode with open. Okay. Now since this is open, so I will be equal to 0 because this is open. Then V output will be equal to 0. Okay. Since no any current is flowing through this load or through this circuit, so V output, it is equal to 0. As this is open, so I is equal to 0. So V naught, it is equal to 0. You can see from time period T by 2 to T, output is 0. Okay. Now for this is from 0 to T, time period T. Then for this cycle also, this is positive and this negative. Again the same case will happen. And the magnitude is Vm. This magnitude and this magnitude, both are same. The difference is that during negative half cycle, since this is in reverse bias condition, so under reverse bias condition, and if we are considering diode as idle diode, in that case it is open. Okay, so open means V naught it is equal to 0. Okay, So this is the working of a half wave rectifier circuit. Okay. Now see, in this figure, this is the input versus output of a half wave rectifier. See, this is Vm, this is Vin, and this is Vout. Okay. So during positive half cycle and during negative half cycle, during positive half cycle Vout is equal to Vin if we are considering diode as idle diode, and during pi to 2 pi, during negative half cycle V output is 0. Okay. So corresponding I naught. Okay. How we can plot I naught? Like similar way, this is Im. Im is the peak value of the current Im. Okay. So this is the graph. Okay. Now how we can determine RMS value and average value. Okay. See, IRMS is root mean square. So how we can determine the IRMS? Okay, IRMS, it is equal to 1 by 2 pi 0 to 2 pi id square d theta. Why it is 2 pi? Because the time period is 0 to 2 pi. This is the time period. This is one time period. From 0 to 2 pi, 1 by 2 pi, it is 0 to 2 pi id square d theta. So finally we are getting it is equal to Im by 2, where Im is the peak value. What is this peak value? Peak value is like this: Im, Vm. This is Vn. Okay. So these are the peak values. So it is equal to Im by 2. So we can say that IRMS value, it is equal to Im by 2. This is for the case of VRMS also. VRMS, it is equal to Vm by 2. This is for a half wave rectifier circuit. For a half wave rectifier. Okay. Similarly, how we can determine IDC? IDC, we can determine it as it is equal to 0 to pi id d theta divided by 2 pi. Okay. So it is equal to Im by pi. Okay. IDC is equal to Im by pi. Now you can see, so VDC, it is equal to Vm by pi. Okay. So we can write IDC, it is equal to Im by pi. IDC, it is equal to Im by pi, and VDC, it is equal to Vm by pi. Okay. So this is for a half wave rectifier. These are for half wave rectifier circuit. So we can calculate VRMS, IRMS, IDC and VDC of a half wave rectifier circuit. Now, what is the efficiency? Efficiency of a half wave rectifier. How we can calculate the efficiency of a half wave rectifier circuit? Efficiency, it is equal to output power divided by input power. Okay. It is output power divided by input power. So how we can calculate it? see, output is DC. Output is DC. So it is output power P out. It is equal to I DC square into RL. Suppose the circuit is like this. We can write this, or we can represent by this. Okay, say this is AC and this is, say, V in plus minus. Okay, this is diode D and this is V out. So P out, it is equal to IDC square into I into RL. Okay, so in case of half wave rectifier, IDC, it is equal to IDC or I average. It is equal to how much? It is equal to how much? It is equal to IM by pi. Okay, now it is IM by pi square into RL. Now P in, input power, that is input power across this input power. Okay, input means towards to the secondary side of the transformer. We can represent a half wave rectifier by using a transformer, or directly we can give input V in, okay, of low magnitude. So P input, it is equal to I RMS square into RL, because see here also input is AC. Input is AC. Here V input is AC, and after the use of this diode, okay, then only it is rectified. This is AC. So P in, it is IRMS square into RL plus, say, this is RL. If it is having some resistance, forward resistance as RL. Okay. So efficiency, it will be equal to how much? Efficiency, it is equal to IM by pi square into RL divided by IRMS square. IRMS square means IM by 2 whole square into RL plus RF, like this. Okay, so it is equal to how much? So efficiency eta, it is equal to IM square by pi square, and here it is IM square, and this is 4 into RL. Here it is RL plus RL. So it is equal to 4 divided by pi square into 1 plus RF. This is RF divided by RL. If we are dividing RL in numerator as well as denominator, then it will be 4 divided by pi square into, it is RL divided by RL 1, and RL divided by RL it is 1, plus RF divided by RL. Okay. Now in general, the diode, this diode, its RF is very less, and if we are considering this diode as idle diode, then in that case RF is equal to 0. Okay, So if RF is very less as compared to RL, then we can write it as 0. Okay, then under that case it is equal to 4 by pi square, which is equal to 0.406. Okay, so efficiency in terms of percent, so you can see efficiency in terms of percent, it is equal to 0.406 into 100. So it is equal to 40.6%. Okay. So the efficiency of a half wave rectifier circuit, it is 40.6% under maximum condition. This is the maximum value of efficiency of a half wave rectifier circuit. Here we are considering RF as 0. It is negligible as compared to RL. Okay, so under that case only this is eta max, efficiency in terms of maximum value, it is 40.6. Then we can see the output frequency. Suppose this is with theta versus V in 0, pi, 2 pi, like this. Output of a half wave rectifier, it is like this, then this, then in this. This is Vm, also this is Vm. This is one time period, this is one time period. So time period of output, time period of the output wave, it is equal to the time period of the input waveform. Okay, so we can say that both the time period it is equal. So F out, it is equal to F in, means this time period it is equal to this time period. This is for the output V out, and this is for V in. Time period, both the time period are same. So we can say that V out of F out, it is equal to F in, means the output frequency it is equal to the input frequency of the signal. Okay, then we will see the ratio of Vrms divided by V average. It is equal to form factor. It is equal to 1.57. So calculate, see, Irms, I average or IDC. It is Irms or IAC. Form factor. F out means frequency of the output signal. Then efficiency, and efficiency in terms of percent for a half wave rectifier. Okay, suppose we have seen like this half wave. This type of circuit we have seen. Now if we replace this diode and we are connecting this diode like this, in this manner, then what will be the output? Suppose this is V peak and this is V in. Where V in? This is V in. Okay, and this is theta, 0, pi, 2 pi, 3 pi, like this. Okay, now for this type of circuit, what will be the output? What will be the output with respect to theta? Okay. Now, see, this is positive half cycle and this is negative half cycle. During positive half cycle, it will be plus here and this will be minus here, just like earlier case. Now, this positive and this is N side of the PN junction, this is P side of the PN junction. Now, for this case, this diode is in reverse bias condition. This diode is in reverse bias condition, so we can replace this diode under ideal case. Okay, so this is open switch. Okay, so in that case, this will be output will be 0 because I is equal to 0. Okay, now during negative half cycle, second case is negative half cycle. During negative half cycle, what happens? During negative half cycle, the polarity at the secondary of the transformer, it is like this, minus plus. Okay, so due to change in this polarity, means this is minus and this is plus terminal. Okay, and here this is V in, and this is N side and this is P side of the PN junction diode. So this is in forward bias condition. During forward bias condition, what happens? During forward bias condition, it is replaced with a short or closed switch. So V in will be equal to V out. So for this case, V out it will be like this. V in will be equal to V out. Okay. Now for this case, it is again V out is 0. For this case, it is again like this. Okay. So in this case, we are seeing that during negative half cycle, the diode conducts, and during positive half cycle, the diode does not conduct. So in ideal case, for reverse bias condition, it is open. Open means V out is 0. During forward bias condition, V output it is equal to V in. So suppose this is minus Vp. So here it is minus Vp. So in this way, a half-wave rectifier circuit works. Okay. So the main function of a half-wave rectifier circuit is to convert AC to pulsating DC. What is pulsating DC? This is AC signal at the input side, and in the output, suppose for the positive half cycle the diode conducts, and for the negative half cycle diode does not conduct. So this is output and this is V peak and this is say V peak or Vm. You can write Vm or V peak. Okay, and this is V in and this is V out. Okay. Now what is pulsating DC? Here it is complete AC signal and here it is AC plus DC signal. In pulsating DC signal, output is pulsating DC. So in pulsating DC, AC component is also present. That is why it is known as pulsating DC. Now this pulsating DC is converted to complete DC by using some filter circuit. Okay. Now as we can see that the output This is Vm. Okay. Now, or V average, it is equal to Vm by pi, and Vrms is Vm by 2. Okay. This is the output waveform of a half-wave rectifier circuit. This is the input that is given to the rectifier circuit. Its peak value is Vm, its peak value is Vm. Now VDC is Vm by pi, this line, and Vrms, this Vrms is Vm by 2. Okay, so we can see that Vrms is more. Vrms is Vm by 2. VDC is Vm by pi. So Vrms is more as compared to VDC in the output waveform of a half-wave rectifier circuit. Okay, that is why efficiency is lesser. Efficiency of a half-wave rectifier circuit, maximum efficiency is 40.6%. Why this is? Why only 40.6? Why not 100%? Okay, so this is the main disadvantage of using a half-wave rectifier circuit. Here the efficiency is only 40.6%. Means if we are giving this AC input signal, so in the output we are getting only 40.6% DC signal, and the rest are not DC. So this is the main disadvantage of using a half-wave rectifier circuit. Here we are seeing in this figure, you can see Vrms is Vm by 2, VDC is lesser. Okay, so efficiency of a half-wave rectifier circuit is 40.6% only. This is the main disadvantage of a half-wave rectifier circuit. Okay, we have seen this diode as ideal diode. Now, if we will consider this diode as not ideal diode, but if we are replacing this diode with silicon diode, so for silicon diode, its V0 is equal to 0.7 volt. Okay, then 0.7 volt. Again like this. This is theta. See, if we are using silicon diode, then in case of silicon diode, V0 for a silicon diode is 0.7 volt. So if this is at 0.7 volt, current will only go across the diode when Vin is more than or equal to V0. Okay, so till 0.7 volt, it is in reverse bias condition. So here we can see that V output is 0 because it is in reverse bias. It is open. So V output, it is equal to 0. Suppose this point is A. Okay, so like this. Then it is not Vm, but it is reduced by Vm minus 0.7 volt. That is here Vm, it is Vm minus V0. This height, it is Vm minus V0, because we are using a silicon diode. Okay, and if we are using simplified model, not ideal model for a silicon diode, then it will be Vm minus V0. Okay, so this height, it will be Vm minus V0. Similarly, this height, it is Vm minus V0.